friends, in this video I will start teaching basic controllers which can be used in industrial process. First, we will have a short introduction to the manual and automatic controls. Then we will take a look at the on-off controllers and their problems. Usually, on-off controllers are used with a deadband. These controllers are used by digital devices which have two states, on or off. On the other side, with application of analog devices, we can design and use the PID controllers. Each industrial process has some inputs and outputs. Simple control methods are independent of the output state. Remember, we did a project with the timers for this tank. Now I am going to show you the problem with a manual control system. Suppose the desired level is 130 centimeters. So I click on this button to start filling the tank. I have to check the level with my eyes continuously till it reaches the desired level. Now I need to click again to stop the filling. As you see, because of a delay in the operation of the valve, the liquid level has reached above the desired level. Therefore, it is necessary to empty the tank a little. The control method, which works with human interaction, is called a manual control system. Therefore, in a manual control system, the performance of the system is highly dependent on the operator. This system has no special hazards, but for high-risk systems, the manual control method is not suitable because of system maintenance and also operator safety. Today, many industrial processes are controlled automatically, and the output status is used to determine the system input. This is its complete diagram, in which sensors and controllers are used instead of the operator. Here the transmitter measures the boiler pressure and the level sensor measures the liquid level inside the tank. And we are using a S7-1200 PLC as the system controller. Let's explain this diagram. Assume that the liquid level inside the tank should be 150 centimeters. So this is the reference value. Here the output we want to control is the liquid level. Also, suppose the level sensor that is connected to the controller shows the number 120. Now, the difference between the reference value and the actual value is plus 30. So based on this difference, the controller knows the actual level is less than the reference value. Then the controller will decide to turn on the inlet valve to increase the liquid level inside the tank. If the liquid level reaches 160 centimeters, depending on the amount of error, the controller will decide to turn off the inlet valve or even open the outlet valve. Now let's determine different types of an automatic control system. Let's start with the simple on-off controller. On-off controllers are used when devices such as valves have only two modes, on and off. Therefore, when the error value is positive, the controller can only open the inlet valve and close it when the error is negative. Note that in this control method, the error sign is important, not its amount. Let's see how this controller works. First, I determine the reference value with this potentiometer. Because the current level of the liquid is less than the reference value, the PLC opens the inlet valve automatically until the liquid level reaches the reference value. As you can see, because of the delay in the valve, the level of the liquid is slightly higher than the reference value. Now let's see the controller performance when the draining valve is open. When the water level drops, the controller automatically opens the inlet valve and closes it again when the liquid level reaches the reference value. As you can see, PLC is constantly trying to keep the liquid level at the reference value, but the liquid fluctuations inside the tank have affected the controller performance. It makes the inlet valve turn on and off constantly, which can damage the inlet valve. Let's see how this problem can be resolved. This diagram shows the operation of the on-off controllers. As you know, this controller opens the filling valve when the error is positive. Otherwise, its output will be off. The main problem is when the error is close to zero, because in the presence of disturbances, such as fluctuations in the liquid, the controller output will be switched between the on and off states continuously. To resolve this problem, we can use on-off controllers with a deadband. Pay close attention to its diagram and this part. The controller output is off until the error reaches 10 centimeters. After that, small disturbances cannot turn off the output immediately because the output stays on until the error reaches minus 10 centimeters. So, with this diagram, small disturbances cannot change the output states. Naturally, we can change this width based on the process and disturbances. Now let's modify the previous PLC program to see this controller performance. This network is the main part of the on-off controller program. When the liquid level is less than the reference or set point value, this number will be moved to this PLC output to open the fill valve completely. Otherwise, the filling valve will be closed. Now let's insert a deadband to this control logic. First, insert an SR instruction. Now insert a subtraction. Instead of using set point, we must subtract 10 from that and then use its result in next comparison. Similarly, when the liquid level is greater than set point plus 10, the filling valve will be closed. Now let's test this program. Let's change the reference value with this potentiometer. Alright, let's choose 80 centimeters. Automatically, the PLC opens the filling valve to increase the liquid level. Tank filling will be stopped if the liquid level reaches 90 centimeters, not 80. Now let's open the draining valve. Then tank filling is started again if the liquid level reaches 70 centimeters. As you can see, the problem of liquid fluctuations inside the tank has been resolved by the inserted deadband to the previous on-off controller. Now let's see what the proportional controllers are. This controller multiplies the error value by a number such as Kp. For example, if the error is 10 and the Kp is 2, the output will be 20. If the error is -5, the output of the controller will be -10. So the controller output is a number that has more than 2 states. Therefore, in order to use this controller, analog equipment must be used. This diagram shows the relationship between the input and output of the controller with the Kp gain. Usually, we must consider some limitations in practice. Sometimes we cannot have a negative value at the controller output because some electric devices only work with positive voltages. So the controller diagram will look like this. In this case, we can use two valves, a filling valve for positive errors and a draining valve for negative errors. The next limitation is the output signal size. We cannot give an infinite voltage to an electric valve, so the diagram of a proportional controller could be like this. Now let's modify the previous project to have a controller with this logic. The inlet valve voltage changes between 0 to 10 when the error is between 0 and 25 centimeters. Alright, let me delete these extra blocks. I need to have an error value, so I subtract the liquid level from the set point value. Now let's find and insert a limit instruction. So if the error is negative, its output will be 0, and if the error is greater than 25, its output remains 25. Now I am going to use norm and scale instructions like the previous projects. If you remember, to have 10 volts at the PLC output, we must write 27648 at the output address. Alright, this is the main part of my PLC program. Let's test this control logic. Now the reference value is 80 and the filling valve is opened completely. As you can see, when the liquid level reaches the set point, the filling valve voltage is decreased until the level of the liquid is equal to the reference value. Alright, I explained on-off and proportional controllers. The proportional controller is one of the three common PID controllers. Now we are going to explain and test the PID controllers. Alright, we saw how the proportional controller could bring the liquid level inside the tank to the reference level. Now we want to check if the controller can keep the liquid level at the reference level when the discharging valve is open. As you can see, if the discharging valve is open, the liquid level starts to drop, and then the controller tries to bring the liquid level to its reference value. If you do this simulation, you will see that the liquid level will be fixed at 90 centimeters. Although the proportional controller didn't have the isolation like on-off controllers, the current level differs from the set point about 20 centimeters. Why and how this problem can be resolved? Again, let's see the proportional controller diagram. In the previous simulation, the reference value was 110 centimeters. In the steady state, the liquid level stays at 90 centimeters. So when the system reaches its steady state, the error was equal to 20 centimeters. Based on this error, the controller sends a voltage to the inlet valve to open it. Finally, the liquid level remained constant at 90 centimeters, despite the output valve is open. Now let's see why the error cannot be equal to 0 in a proportional controller. Assuming it to be 0, the output of the controller becomes 0 as well, and then the filling valve is closed. This state decreases the liquid level because the discharging valve is open. So the reference value and the liquid level are not going to be equal. This means the steady state error cannot be 0. This is the proportional controller's weakness. Therefore, in the industrial process, the system integrators and engineers prefer to use the PI controllers. Let's see what a PI and PID controllers are. PID is an abbreviation of proportional integral derivative. I've explained the proportional controller earlier. If the integral of the error is added to this controller, then we will have a PI controller, And also if we use a derivative of the error in the formula, then we will have a PID controller. First, let's explain the PI controller. Suppose the reference level is 110 and the current level is 90. At the start time, the error is 20. The elapsed time is 0, so the integral output will be 0, but the proportional term will send the voltage to open the filling valve to increase the liquid level. Now suppose the error is 10. Now both proportional and integral terms send the voltage to the filling valve. Similarly, this process will be continued until the liquid level reaches the reference value. Here we can see the important difference between the proportional and the integral terms. When the error is 0, the output of the proportional term is 0, but the integral term uses the past error values, so its output can be non-zero. Therefore, unlike the proportional controller, the PI controller can open the filling valve sufficiently when the error is 0, so the integral term compensates for proportional weakness. The PI controller has a small problem that can be ignored in most industrial processes. When the level reaches the reference value, due to the integral term, the filling valve remains open, so the liquid level rises again. When the error value is negative, the system will try to return to the reference value. Therefore, the integral term causes the controller output to fluctuate slightly, which it disappears over the time. Note that at the beginning of a process, the size of the error is large and the elapsed time is small. Therefore, the output of the proportional term becomes larger, which has a major role in the controller's performance. As time goes on and the error size decreases, like in this example, the proportional output becomes closer to 0 and the integral term determines the controller output. Sometimes the derivative term is used in the controller to eliminate the fluctuations caused by the integral term. Like the integral term, try to understand how the derivative term works. For many industrial processes, we can achieve a suitable controller by adjusting these coefficients. This figure shows the effect of each coefficient for a tuned PID controller. Now let's design a PID controller in TIA Portal. Here we have a level meter and this valve which is connected to these PLC addresses. Here the second network of my PLC program converts the level sensor signal to a number between 0 and 300. This number indicates the liquid level in centimeters. The easiest way to implement a PID controller in the TIA is to use the PID instruction. To use this instruction, first click on Add New Block, then select Cyclic Interrupt and determine its time like 500 milliseconds. Pay attention, we don't call this organization block from the main block because it will be executed every 500 milliseconds automatically. Now from the right list, insert the PID compact instruction in the created cyclic organization block. This instruction needs a data block to work. At its first input, the set point value is defined. At the second input, a variable of the user program is used as a source for the process value. Here I can use the computed liquid level. That's a number between 0 and 300 centimeters. The third input pair, should be connected to a PLC analog input as the source of the process value. Pay attention, the PID controller will use only one of these two inputs, which must be specified in its settings window. Well, this block has three outputs. Output is a number in real format, output pair for PLC analog outputs, and output PWM to have a modulated pulse signal. Let me use this PLC analog address, which is connected to the filling valve. Now let's go to this PID setting. First, the type of the process under control and its measurement unit can be selected. If necessary, the output signal of the PID can be reversed. In the help window, we can see this controller information like its operating modes, the used mathematical relationship with its parameters description, and also its diagram. For example, inverting the controller output is performed here. Alright, let's select the automatic mode and go to the next step. Here the inputs and outputs that are explained before must be selected. Now I need to modify the input range. Remember, the liquid level inside the tank is a number between 0 and 300 centimeters. This part is disabled because the analog input has not been selected before. Also, if it is necessary, you can change some outputs settings, and finally you can see the PID parameters. To improve the PID performance, these parameters must be tuned. First, let's test the PI controller performance with these default settings. Pay attention, you may not be able to simulate the PID controller on your computer like in the previous projects. To resolve this problem, which happened only in the simulation mode to me and others, you either have to use a real PLC or use the PLC sim simulator with a 1500 CPU in the hardware configuration. First, I'll test the PID controllers with the PLC sim simulator, and then I will use a real S7-1200 PLC. Alright, first I need to find and open an appropriate PLC sim 1500 template, which can be downloaded from the Factory IO website. After all this, I have generated the PID program in a cyclic organization block again. These two bits are used to activate the PID controllers. Also, after transferring the program to the virtual CPU, we have to change the Factory IO configuration from S7-1200 to S7-1500. Now the Factory IO is connected to the program on the virtual CPU. Let's go to the online mode. Based on the program, I have to activate the PID controller. First, let me change this auto manual selector. The next contact is activated by a switch from the HMI, which has been designed before. Let's activate the PID controller. Alright, as you can see, the PID controller is activated. I can change its set point from the HMI screen. Let's select 150 centimeters. As you can see, the PID controller output is activated and it turns on the filling valve. Well, this display shows the liquid level. Also, on the Design HMI program, we can see the level liquid and the set point diagrams and also the PID parameters at the bottom. As you can see, as the water level passes the reference value, the controller starts closing the inlet valve. Now let me open the discharge valve for 50%. If you simulate this program like me, you will see that after a time with a little fluctuation in the water level, the controller can fix the water level at the reference value. Now click here to see how PID coefficients can be tuned by the TIA software. Click here to start sampling and to show the process and reference values. Here select and start pre-tuning. Alright, here is an error at the startup of the tuning. This process value is too close to the set point. To resolve this error, let me stop factory I/O to empty the tank and then start it again. Now the reference value is 150 centimeters, but the current level is 0. Let me start the pre-tuning again. As you can see, the TIA modified the PID coefficients. Well, let's use these PID coefficients to control the water level with my S7-1200 PLC and HMI. Notice that in the manual mode, I can control the two valves with these two potentiometers. Let's go to the automatic mode in which the water level will be controlled on the HMI. Notice that on the HMI screen I can choose what percent the valve must be open. Now let's activate the PID controller with the previous coefficients. As you can see, the controller tries to reach the water level to the desired level, which is 50 centimeters. Now the level is higher than 50 centimeters. In other words, the error is negative. So the controller decreases the inlet water volume. Now the water level is lower than 50 centimeters, so the controller increases the water inlet volume. Notice that the PID controller tries to keep the water level at the desired level. Now the water level is reached the desired level, which is 50 centimeters. If I change the desired level, the PID controller tries to bring the water level to my desired level as well. I hope this video has helped you to understand the concept of the PID controllers. Now let's learn recipes and alarms in an HMI display programming. Alright, let's see the previous project. We have learned to change any parameters on the HMI screen. Now we are going to see how the status of two valves can be changed at the same time. Therefore, we will be able to change the status of any number of variables such as PID controller coefficients at the same time. To do that, on the left side, click on Recipe. Here we can create a recipe and choose a name for that. I want to change the valve states. Pay attention, each recipe has a unique number. In the bottom window, the desired parameters are selected. Here I select the field person tag of the PLC program, which is related to the filling valve. Similarly, I select a PLC tag related to discharging valve. In the next tab, Data Records, we specify desired values for each selected parameter. Here, each state has a unique number. For the first state of the recipe, let's open the inlet valve and close the outlet valve. For the second state, let's open both valves for 50%. Finally, for the third state, let's close the inlet and open the outlet valve completely. Now let's save this recipe with 3 states and get back to the tank screen. I want to use some buttons to apply each state's values to my PLC program. Well, in the Events tab, select this function, Set Data Records to PLC. This function selects a recipe with its number. Note that each defined state has a unique number, so this function uses state 1 values for the selected parameters, which are filling and discharging valves. Similarly, let me use two buttons to select other states. Let's simulate this screen. Alright, as you can see, I can change the state of two valves with these three buttons. Here is a problem. Before, we have seen and changed the state of two valves with these numeric I/O fields. Now, we just see 0. Why is that? Pay attention, this numeric I/O field and this button are using the same tag of PLC address, which is field%. This PLC tag is used in the recipe as well. Let's go to the HMI tags table. When we use a PLC address for the first time in the HMI, automatically the HMI defines a similar tag for itself, which is connected to the selected PLC address. Here we are using a PLC address, a field% tag, and also discharge % for two elements in the HMI. To resolve the previous problem, we must define a new HMI tags and use them in the recipe. Pay attention, the old and new HMI tags are connected to the same PLC addresses. Let's go to the recipe and replace the tags with new HMI tags. Now let's test the recipe. Notice that the previous problem has been resolved. We can change two valves states and also see their values on the HMI. Also, we can define recipes on the HMI screen. From the Control tab on the right side, insert a recipe on a blank screen. If you simulate the HMI screen again, this screen will be shown, which can be used to see, create, modify, or delete recipes. For example, let's change the parameters value in the second state to 0 and save the recipe. Alright, what is this yellow triangle and what these messages are? Now we are going to learn to use alarms on the HMI screens. The alarms are messages which will be shown automatically when a special condition occurs. Now if the water level reaches 250 centimeters, a warning text will be displayed on the screen. As you can see, this number is still 0. Now, if the water level exceeds 290, the HMI will show an error text on the current screen. Naturally, the interference value must be closed in this condition. So the lower number of the yellow triangle indicates the number of the current system errors which has been inserted here too. If I open the outlet valve, the water level starts to drop. Now the error has been removed, and when the water level returns to less than 250 centimeters, the warning text will be erased from this screen. Now let's see how the error or warning alarms can be defined on the HMI. We want to show an appropriate message on the HMI screen when the liquid level is lower or higher than a normal level, and also when we activate or deactivate the PID controller. So click on the HMI alarms. Select this tab to define analog alarms. Click here to create a new alarms. Here we can write an appropriate message which will be shown on the HMI. I want to use this alarm when the liquid level is lower than 10 centimeters. In this column, the class of alarm is specified. Here there are 4 predefined classes. Let's select the error class. Because 10 centimeters is too low, then I connect this alarm to the level liquid tag. Here we write the critical level. Finally, we must determine its limit mode. Let's define another alarm when the liquid level is lower than 50 centimeters. For this alarm, I select the warning class. Similarly, I define appropriate alarms when the level is higher than the normal level. To define discrete alarms, we need a word address of PLC memory. So let's go to the PLC tags table. Now let's define the alarm word tag with MW200 address. As you know, a word address has 16 bits. Alarm condition must be written in the PLC program. The first discrete alarm is when the PID controller is activated. So I use the PID activator tag and save that on the first bit of the MW200. Pay attention, the MW200 is included in the M200 and M201. The address of the first bit is M201.0. Similarly, we can define the other discrete alarms. With a word of memory, we can define up to 16 alarms. Now let's transfer this program to the virtual PLC and get back to the discrete alarm window. Now discrete alarms can be defined by the word memory. The first alarm is when the PID controller is activated. Here I connect alarms to a bit of the word memory. Now it is the first bit memory of this selected address MW200. Similarly, we can define the next alarms. Now we need to create a blank screen to show alarm messages. Now just enter the alarm view from the right list. Here we can change some settings of the inserted alarm view. To view errors on all screens, go to the global screen and use alarm elements like the way I am doing. Alright, we have tested this project before with the TIA simulator. Similarly, I can use my PLC and HMI to test the program. As you can see, in the manual mode, I can control the two valves with these two potentiometers. Let's go to the automatic mode, which the water level will be controlled by the HMI. Note that on the HMI screen, an error message has appeared, that is, the water level is too low. Also, I can change the inlet-outlet water volume with the S1, S2 and S3 buttons on the right side of the HMI screen. I can see and manage all recipes on the HMI. If I click on this button, I will be directed to the alarm screen to see all alarms and errors which have occurred until now. As you can see, if the water level exceeds 290 centimeters, the HMI will show an error message to inform the operator. I hope you have learned what the recipes and alarms are in an HMI display programming. Thanks for watching this video.